but I don't have an answer for that. So you have to ask me if you have any question on this stuff. Please okay. So we start with Newton's second law, and we integrate it and both sides with dx. Okay. A is actually dv over dt. Okay, if we do this integration for both sides, we see that we get W net equals to delta K, the work kinetic energy theory. Okay, and then we see that the W net, the work done by all the forces, it can be evaluated by adding the work done by all the different individual forces. So we put them into two categories. The work done by the conservative force and the work done by the non-conservative force. Okay. And here the work done by the conservative force. From that, we can define the potential energy change, delta U equals to negative W and C. Okay, and we cannot do that for non-conservative force. And okay, so now we use this to evaluate several conservative force and give them the form of the potential energy. Okay, any work done by the non-conservative force, you can replace it by a potential energy change, delta U. Okay, so we have only two kinds of conservative force. Okay, in this class, which two?
Gravity and spring.
Gravity and spring force. Okay, first gravity. We are going to do gravity. Okay, but before we can do that, we have to extend our definition to 3 dimension. Okay, we introduce this in terms of 1 dimension. For 1 dimension, the definition of the work, if it's a variable force, so W equals to F multiplied for any particular force, integral of F with respect to the position. Okay, if this is a variable force. If we have the constant force, okay, this is reduced to W equals to force, the constant force, you factor it out, and so integrate the position only, you get the displacement, okay, or you can write as F multiplied by D, the displacement. So this is for constant force. Now, let's look at for 3 dimension. Okay, this is 1D. And now, let's say for 3D, to extend, first look at the constant force. Okay, you can extend this equation to 3 dimension or vector form. So what can we do? W in this case, if it's 3 dimension, you simply replace this algebraic multiplication by some kind of vector multiplication. And we want to form a scalar, right? Work has to be a scalar. Okay, it's related to energy. So it has to be a scalar product. So work in vector form can be written in this form. Okay. So this one, the algebraic multiplication is actually a special case of this inner product or dot product. Okay. So this one, of course, by definition, can be written as F multiplied by T multiplied by cosine theta. This is magnitude of the force. This is the magnitude of the displacement. And cosine theta, here theta is the angle between the force and the displacement. Okay. Now, if we look at the gravitational force, let's try to evaluate the work done by the gravitational force. Okay. So, for example, initially, the object is at some initial position I. Finally, it ends another position F. Okay. So it can along any path. So we can try to evaluate from the straight line path. But please note that for conservative force, the work is independent with the path, right? So actually, along different paths, your evaluation will give you the same result. So now let's look at if we along this path. So this is the displacement. And what is the direction of the force? Gravitational force. Say again?
Downward.
Downward. Okay. So this is the gravitational force. W. Okay. This is. Let's use Fg. Okay. So here, because we need to use W for the work, equals to mg. That's the gravitational force. And this is the angle between them, right? So now, if we want to evaluate the work done by the gravitational force, so it will be, okay, let's say this is the initial position x, I, y, I. This is x final, y final. Okay, so coordinates of the 2 points. Now, the work should be the force F multiplied by T multiplied by cosine theta. So the force is mg. This is the distance. Okay, multiplied by cosine theta. If we know the distance and cosine theta, we can evaluate this. But on the other hand, if we draw a triangle, okay, you can see the distance or displacement multiplied by cosine theta is exactly this one, right? Okay. And this is the vertical distance or delta y. So this equals to mg multiplied by delta y. Okay?
Could you repeat that? About what the dotted lines again?
This is not that even. Okay, this is just in this equation. That's the algebraic manipulation. So this is just normal product. And d multiplied by cosine theta. D multiplied by cosine theta is this delta y, right? So you can see that actually this value only depends on the vertical change delta y. It has nothing to do with delta x, okay? Because from the definition, d multiplied by cosine theta will give you delta y. So it only the work done by the gravitational force is only determined by the vertical change, okay, in the position. So in other words, if you have some initial point here, if they goes to the same height with from different paths, all of them will give you same work done by the gravitational force. It's only determined by the vertical change in the position. Okay, any question here? And of course, this one can be written as, okay, mg okay, let me see. Y final minus Y initial. Okay, so here, in fact, I should say this is my initial position. This is my final position. Because usually we say final position is higher than the initial position. Okay, so the distance is this direction. This is the force. Okay, and in this case, you have to add the negative side here.
Well, because it's going down.
Hmm?
Because it's going down.
Okay, because usually we should call the lower position is initial position. This is the higher position. So the positive direction for y should be defined as this, right? This one. Okay. So in this case, you have to add a negative side here. Okay. So then, from that, W equals to negative delta U. So this is negative mg y final subtract mg y initial. So of course we can define this should be U final subtract U initial. Okay. So we can define the potential gravitational potential energy as mgy. So this is the gravitational potential energy. Or sometimes you can write it Ug equals to mgh, okay, the height. And one thing I would like to mention is that this height is relative to the initial point you set. Okay. Usually we measure the height from the ground, but you can choose any point to measure the ground. For example, like here, if it's 2 meters above the ground, you can also define it from the tabletop, so it's just 1 meter above the tabletop. And you can see that this wouldn't change the work or the potential energy change you calculated in the equation, because it depends on delta y, the change in the vertical position. So no matter where you are going to set it as your 0 point, finally when you calculate the change, it will be the same. Okay? So that's the gravitational potential energy. That's how I arrived at this important definition. And then, now let's look at the work done by the variable force. So here, again, for one-dimensional work, we have the integral of the force with respect to the position.